Right. My name is Oluwole Oyebamiji. So I'm from Lancaster University. I'll just talk a little bit about my background before I move on to today's talk. So I completed my PhD in 2014, and after then I did a 3-year postdoc at Lancaster University. So I was working on a project on kind of biological simulation. So we are trying to develop agent-based model for simulation of microorganisms, the kind of bacteria you find in wastewater. So to do the, nature of job, we've got to run like millions and millions of particles, bacteria, and to do that, it is actually very difficult to simulate that numbers of cells. So we need to introduce something like a statistical approximation in form of a statistical emulator. So that was what I was doing. So we were able to run the model to get like maybe 10 of 6 number of particles, and from there we use statistical emulator to scale up to desired amounts, the number of required number of particles. Then around this time last year, I moved to Lancaster Uni. So I was working on another project called this Statistic, Data Science of the Natural Environment. What we are doing basically on the project is to develop a new methodological approach and new data science techniques to address our environmental challenges. So we are focusing on 3 different problem areas. So we are working on the IC modeling, air quality problems, and the land use scale problems. And the way we run the program is, so we divided the 3 challenges into like sprints. So on each sprint we work for about 4 months. So we've do some a little work on the air quality and IC modeling. So now we are working on the land use scale, and that's one of the reasons. So I'm going to take you through little things we've been doing for some time now. So we start working on these landscape problems about 2 months now. So we still got like 2 more months to go on it. So it's still a work in progress. So you might not really expect any fantastic results. All right. So the topic is uncertainty quantification in high-dimensional landscape problems using these hierarchical models. All right, so I'm going to follow this plan in my talk. So I'll talk a little bit about the kind of problems we are addressing. Talk about the IAP2 data, which is the data I'm going to apply the new techniques upon. Then talk about the challenges and tasks of addressing this kind of problems. Then I'll talk about the methods and then look some conclusion. All right, so the background: to ensure sustainable management of land resources, there is a need for an integrated framework to support policy in understanding the trade between alternative land uses and many policy actions. So we all know different sectors compete for land resources, land allocations, and policy makers, decision makers, to make effective decision concerning all these kind of problem, there's usually involved a model that can be used as a kind of supporting tools to address such problem. So already there are existing integrated assessment models which have coupled together multiple sectoral models to simulate land use change at the global, at the European levels, at regional, on different levels generally. But the problem is usually that there is always a kind of missing process, maybe in form of interactions, feedbacks between land resources and sectors. The other uh, concern again is also the kind of assumption that they are making when they are building some of these models. So beside that, there is also the kind of sensitivity to drivers and the sources of uncertainty. So some of these things they don't even test them. Or all these uncertainty conditions they are not usually robustly, check and test the implications and their effect. And in addition to that, even most of these models they are developed on more cost scales, and we all know that most of the management decisions are often taken at the final spatial scale. So all these kind of things they are kind of challenges to properly address these kind of problems. So decision makers and other stakeholders need reliable science-based information to help them respond to the risk of climate change impacts and opportunities for adaptation. So in other words, there is a kind of integrated methodology that can be used to assess this cross-sectoral climate change impacts, adaptation, and vulnerability. So one of such models that has been very successful in coupling different sectors and have been used is this IAP2 model, which we call Integrated Assessment Platform. These are extension of climate-safe model, and is kind of based on ensemble of different meta models which are run with the user. Selected climatic data representing the present and the future climates. So this is a schematic diagram of the IAP2 models. So we've got in different sectors. The models take climate as an input, some socioeconomic scenario, then soil, and it couple different sectors doing different to represent different processes. There are interactions and between some of these sectors. For instance, if you look at maybe spatial crop allocation across maybe Europe, for instance, it's not only determined by maybe the amount of food demand, it also depends on the competition between maybe the urban and the forestry. So depend on the flooding, which is kind of maybe the land suitability. So if you look at that, you also see that that's also affecting the biodiversity, affecting water use. So all these kind of models were able to assess the kind of interactions between different processes. So what we've done is we want to try and quantify the uncertainty using this data from this IAP2 model. So we've developed our large hypercube sample. We have 27 parameters, and out of those parameters, 20 of those variables are continuous and 7 are categorical. We did 2,000 runs, and we were able to get some data. So each run represents a map, European map of some of the outputs, which in the next few slides I'll be talking about. And to do that, we have so many scenarios we are looking at. So we've got in time, we've got in emission, climate model, and socioeconomic scenario. And in our socioeconomic scenario, we have these 4 different words which they are used to, trying to explore the kind of how the future world is going to evolve, or how the future world is going to look alike. So they are kind of choosing to, reflect how those changes, how are they going to affect our adaptation, and how is that going to also influence the kind of maybe the vulnerability to the climate change. So next slide, I'm going to talk more about these 4 different scenarios. So in the data set, we also have 3 different time slices. We have 10s, 20s, which is this range, 2050s, 2080s, this range. And data is such that we also have baseline, which is average between 1961 to 1990. So they are kind of the change relative to that baseline. We've got three emission scenario: RCP 2.6, 4.5, and 8.5, and we are using 10 different climate models. So this socioeconomic scenario, I'll just try and explain a little bit more about that. So they are kind of first selected national socio and economic socio and economic scenario is going to look in the future, and we've gotten four of them. We are the world, which represent a kind of maybe prosperous future world whereby you have a kind of maybe economic development and growth, rapid economic development and growth, and you have maybe stable political and social situation. So in under this type of scenario, everything it's not really a perfect world like that, but things are better economically, social, and politically. And we also have Icarus, which represent a kind of contrast to that, where the economy is kind of struggling, and it also leads to kind of maybe social unrest, which then result in a kind of maybe political instability. And we have should I stay or should I go, which represent. So under this scenario, we still have kind of the economy is still relatively okay, but the situation is a bit more precarious, and like you don't really know whether things are going to change or whether it's going to remain the way it is. So it's kind of uncertain or unstable world. And the last one is riders on the storm. This one, there is also an economic problem, but this is easily counterbalanced by the political will by the actors to maybe trying to counterbalance the effect of that economic problem in form of maybe investment in green energy and some other things like that. So the output from the model. So we have around 100 different responses. We've carefully selected about 20 for voting. And those outputs, you can also categorize them. So we have those that are land use related variables like area of variable land, area of intensive grassland, area of extensive grassland. We have some that are food production related indicators. We have biodiversity change, which in form of maybe like biodiversity vulnerability index. So we have different categories of those output like that. And like I said, so each of those runs is a map about 23,871 pixels on 10 by 10 degree, and that's around 16 kilometer by 16 kilometer resolution. So this is just a sample example of baseline hierarchical crops. So, and you can see there are a lot of spatial variability for this output. I've got another example, this land use diversity. So this one too, we also see there's variation across the space. And so what actually do we want to achieve with these sort of things? So what we want to do basically is that we want to build a new Bayesian hierarchical modeling framework. We want to test the newly developed techniques on the IAP2 data. And we want to also decide on what is the appropriate outputs that may be of importance that we want to consider. And the kind of strategy we want to use for the modeling. So we've carefully selected 20 outputs, and that 20 dimension is to us kind of very big. So we are looking at doing a kind of dimension reduction using method like EOF, empirical orthogonal functions, or principal component analysis, just to reduce the dimension. So Bayesian principal component is one technique that we have explored so far. good thing about this technique is that unlike the standard principal component, where you have to maybe manually determine the number of components you want to use. So this one it's automatically selected the number of components using a form of cross validation. We would also like to explore other relevant techniques like random projections, online learning algorithm, then parallel covariance computations, and some other things. And within our Bayesian hierarchical, we want to, because of the dimension of the data, because of the nature of the data, they are quite very huge. So doing standard Bayesian is going to be very problematic. So we want to try to explore a kind of a sparse Bayesian process and maybe nearest neighbor Bayesian process within our hierarchical framework. So this I'm just showing a sample result from principal component. So we've applied principal component on some of the scenarios, and we've selected 4 pieces, and we try to look at the distribution of these 4 selected pieces here. They are not, I think the first one is not really normal, but the other 3 we can easily maybe, we just want to explore their distribution before we start our problem. And we also try to look at the percentage of variance or the proportion of variance explained by each of those components. So this one, it also enables us, it's a kind of guide on where do we want to stop. Okay, does what that model has given us, probably maybe ask you to select 2 or 3 components, does it really work? So we want to look at, okay, what is the percentage of variance that each of those principal components were able to explain. Now, so to the model now. So we are using hierarchical modeling techniques, and what that basically means is that you've gotten some data which is conditional on some process and some parameters, and that process is dependent on some parameters, and our parameter is given in form of the prior information which we know, right? So our model now. So we try to feed this type of model to the simulation run we've gotten, where we have our Z RPS given as Y RPS plus epsilon RPS, where RPS can further be decomposed into X RPS beta plus eta RPS, and I will quickly explain this. So the high AP2 model is a kind of so it's not like a standard simulator. It's actually like an ensemble of different emulators. So in other words, what we are actually doing, we are not trying to emulate a simulator. We are emulating an emulator. So that's the way the problem is, because most of those processes have been replaced by their emulated version. And so in other words, we can assume that maybe the kind of data we get there is not actual data. So if we assume that the data we've gotten from high AP2 is maybe it's given by maybe the real process and some maybe random error, and the real process we further decompose it into form of maybe linear trend, and there's some maybe spatial stochastic process. And so let's set RPS be given by this form, the noisy graded simulation data from high AP2 model. And let YRP represent the actual simulation value corresponding to ZRP. And each R varies from 1 to n, it represents different scenario, and P is 1 to P, denote different parameter combinations. So remember, we've done 2,000 runs, and we have 4 socioeconomic scenarios, then we have 3 emission scenario. We've got also like 10 different climate models. So here we just take some sample of the data, and we are trying to feed this model just to test just to demonstrate the kind of things we want to do. So our eta RPS are specific temporal random effects, and epsilon RPS is the pure error term, or which they call nugget in some folding framework. So we assume that our random error and the spatial random process are independent, and which are given this normal distribution, normal 0, eta tau square I n, where my high is there, or identity matrix, diagonal matrix, and we also have the eta RP as normal 0, sigma, eta respectively. So my CSISG, that's the Martin correlation function. And my covariance function here, I can rewrite it in form of sigma square C, where my sigma square is just like a maybe homogeneous spatial variance. My XRP is the matrix of covariance, which represents some of the climatic variables and some of the parameters we vary in our Latin epoch. And all our known parameters, we can combine them as theta. So we have the following parameters we've got to estimate: beta, sigma square, tau square, phi, and none. Right. So we can easily write the joint posterior distribution for all our parameters, and is given by this equation: log p of theta comma y given z is proportional to this long equation, and our pi of theta denotes the prior distribution for the parameters. And since the aim of the analysis is actually to predict, maybe we've run our scenario at some parameters, settings, or combinations, and we want to predict at some point where we've not even run our simulator. So our predictive model can be given by this. So now we want to find the prediction at this point, at new points, given the data we already have. So it's given by this integral, where our highest node knows maybe the new locations or where you've not currently run your simulator.
Olu, just so you want to predict the observations and not what's actually happening there?
Not the observation. We want to predict. We've gotten some training set from the simulator.
Sure.
Right. So we want to test the performance of the emulator on some points where we've not run our simulator.
Oh, right. So that these are left out points.
Yeah.
Okay.
Is that clear?
Mm-hmm.
Right. So we are not doing anything about observations. So it's just purely simulation of data. We are fitting model to it, and we want to test the performance of that model. Right. So then, all right. Okay. So this joint posterior. So some of these parameters, their conditional distribution can be obtained in closed form. I think except this far. So which we are using a kind of maybe metropolis algorithm to sample from. So and the sampling algorithm, the way it works is that we can sample all the theta and the y from our joint likelihood. So having gotten that, then we can sample y. Y is the kind of the real process from the conditional distribution of y hierarchy S mu, given that we use otherwise. then we can then sample the noisy output, for instance, now from this distribution. So we've implemented this using some C++ with RCPP packages in her and RCPP Amadilo library, which is kind of very nice, or linear algebra library in her, so which kind of make it a bit more faster to run, and we can also, make use of thread parallel computation. And so some results now. So here I'm trying to, we are comparing some of the simulation results with what the model is giving us now. So this is a particular example from, so the output is managed forest, and it's under this, we are the world scenario for 2050s. And this is my simulation, this is my prediction from the emulator, and we've gotten some deviation, which is the represent the kind of maybe the uncertainty in our predictions. And here is the difference between this and this, between the prediction and the simulation. And when we look at it carefully, we think the model is doing a very good job. So here is another example again. So here we've gotten water exploitation index, and so this is simulation from their IAP2, and this is the prediction from the emulator, the model we are fitting. And we've gotten the deviation, which is square root of variance, which represent our degree of uncertainty, and we've got the difference between the prediction and the simulation. So this also still does same, we are the worst scenario, and for year 2050s. So generally, when you look at this, you see that the variance kind of very large.
That's two in a row where the variance, the deviation has this like really weird structured horizontal thing going on.
Yeah, that's what I want to comment on. So, because we don't actually model the original output from the model, so what we've done is we've modeled the PC output. All right, and this variance we've tried and add the reconstruction error because we've moved back to the original scale now.
So the PCs are that structured, the left out PCs are that structured?
Yeah.
Does it have something to do with the spatial term from your earlier model? Like the structure in the deviation, does that relate to the spatial term on your Y, or?
Yeah, I think I think because the PC didn't explain everything, just some percentage of the variation in the original output, right? And what we've done since we've selected some of those pieces, discuss. I think this we are using maybe 4, and like I saw one of those so the 4 we are okay. Yes, we've selected about 4, which is explaining I think less than 80%. Oh, sorry. Yeah, explaining about 80%. So we have some residue that we cannot really explain. Yeah, so to quantify our uncertainty, the total, our total uncertainty will be the kind of uncertainty we get from our emulator. In addition with that, the uncertainty we get when we change our scale from the original scale to the PC scale. So, and that is what and that's what we've added here.
But I mean, it just seems I don't see any physical reason for having an EOF or combination of EOFs that would be that stripy. You could imagine it might be scaled north to south, but it just seems like there are horizontal lines going across, and they're different every time, and that's not, you wouldn't normally see that in even low order EOFs of some sort of spatially continuous model.
Yeah, you could be right. This, like I said, is still work in progress, and it's not a final result of whatever or what I want to do. So I'm going to check that.
It's interesting.
Yeah, that's one of the reasons why I'm presenting here, so I can also see people's opinion and learn more about it. Yeah, thanks for that. Right, so these are some of the things we've also put down that we want to explore. So there is no integrated assessment models of land use change currently exist for the UK, which is physically explicit and respond to multiple interactive drivers. So I don't know if that statement is correct. So one of the things we want to do is that we want to test the applicability of our emulator at the UK scale, because that model is European scale. And in order also, we want to use that emulator to downscale to UK scale. We also want to quantify uncertainty as we move from one spatial resolution into another. So the other thing we want to do is that we want to find some observation data to calibrate that model with. And finally, that IAP2 model, we also have the Scottish version of it, so which is also going to be like a kind of a very good way to also validate our results, since we have the Scottish version. So if we downscale to the UK scale, so if anything goes wrong, we can easily test with this Scotland version to check whether our result is reasonable or not. And so that's the end. Thank you very much for this.
So questions, comments, suggestions?
Many questions, but I don't want to dominate the whole time. With the variables, you've got 20 continuous and 7 categorical variables.
Right.
Yeah, so that's, how have you, okay, well, in your covariance function, are those categorical variables going in just kind of in the return in terms of some difference, or are you using some of the stuff on categorical emulation?
What we do is that, even the LHS, what we do is that we use a two-stage sampling stuff. So for the continuous, we sample them differently than the categorical. We do it using a kind of maybe random sample. So we divide because the variables, we can't sample them together because one is continuous, one is categorical. So the continuous one, we use the LHS. The categorical one, we sample it randomly because they are just 0, 1, 2, 3. And in our covariance workshop, we also divided them into 2. So we have one part, which is handling the continuous part, and we have the other part that is handling the 7 categorical parameters.
But there's a covariance.
Yeah.
It's not like 128. I think that's 100. It's not 128 separate emulators.
Oh, no.
Okay. What's the separate part? Not the return.
Sorry, what is it?
The separate. So you showed us the emulator. You showed us the return covariance, right?
Right.
But that's not. You just said that that's not what you were using for the categorical. I just wondered what you were using.
Okay, you mean? Yeah, this is the matter. I don't get your first kind coming.
So that's inputs are space and time, right?
But we are not including the time now. So in this analysis, it doesn't include time. It's only space.
Okay, so let me ask it a different way. If I gave you a new value of 20 continuous inputs and 7 categorical variables, how does your model predict IAP2 from that?
Oh, no, okay. I got your question. Okay, so what happened is that we've gotten two sets of inputs. I said we have 27 parameters. 20 are continuous, 7 are categorical. Right. So those 27 parameters, actually, they don't vary spatially. They don't vary spatially. And what we've gotten as an output is spatial result. So they were not used to train the emulator. So what was used to train the emulator is some climate input. You see, I put some climate here. So the climate data are spatially resolved, right? So we've got the temperature, minimum temperature, maximum temperature. I think precipitation as well, so 5 of them. So because they are spatially resolved. So if you want to include those 27 parameters, they are not spatially resolved, so they are like, it's not doing anything. I don't know whether you get what I'm trying to say.
I have a different tack, but I'm not sure it's very helpful, so I probably shouldn't say it. But you know, you've taken models, some of which I'm familiar of. Well, the IEP does takes models and then it produces emulators for those models and combines them together.
Yeah.
And then you're making an emulator of that emulator. So you've got an emulator of emulation models of models of underlying processes. When is enough emulation? You know, when does that sequence of modeling and emulation? When do you decide that there's too many degrees of freedom, too many error terms being introduced at each stage, both in terms of processes missed, in terms of variability in data? You know, you know, do you see what my concern is? That it's still far from the underlying system. But you know, if you had an emulator, this emulator, would that be okay, or not?
Yeah.
How do you decide?
Yeah, actually, that's one of the things that make it a bit more challenging, because, like I said, it's not a kind of proper, like a standard simulation data. So what you've got you can, there are different approaches that one can isolate it, but one of such is we've just assumed maybe, okay, it's a noisy data we are getting, we are not really have access to the actual data, because that simulator has been replaced by the emulated version, and that is what you are basing your analysis on it. So there are already some inherent uncertainty from that process.
Sure. So I'll rephrase it as a better question. When do you decide that it's not possible to continue this chain of emulation? Is there a point that you decide that you're too far away? I guess that could be expressed as a mathematical question. I don't know what the answer is, but
Isn't it a better question? I mean, emulators just give you predictions for slow functions. Isn't it a better question to say, was sticking emulators in here everywhere but still creating a model that was too slow to run without an emulator a good idea?
I mean, I say some of these models are quite slow to run, but they're, you know, the more you know about a model, the more skeptical you become about the results of it, I suppose is the way of putting it. So what's being emulated is flawed in many ways. And yeah.
I agree, but I guess you're getting at so you put all these emulators in at the start, and then if you think about last week's stuff, you increase the model discrepancy so that the model's now further away from reality.
But that's exactly what I'm describing.
Yeah. So then, yeah, I guess so. I see what you're saying.
Any more questions? so we've got, do you want to introduce yourself now? It's going to work.
While you're setting up, could you just, so just going back to the 27 parameters, if I give you a new value of them, do you predict all of those spatial fields? I just didn't understand when the emulator bit happened.
Okay, but let me make it more clear. These 27 parameters were not used to train the emulator.
Right.
They are just used to generate the output. However, because these 27 parameters, they were varied, and we have some spatial climate, so we find a kind of one-to-one mapping from that spatial climate variable, and some of the outputs we've gotten from these models.
Right.
I don't know whether you get what I'm trying to say.
I think it sounds like you varied the parameters to get variance on your observations, and then you use that as if it was just like a pure noise. So they're modeled by the random effects in some sense in your set. Is that what you meant?
Yeah.
Yeah. Okay, I get it. Thanks.
Is that clear?
And yeah, I think so.
Maybe after, if you
Yeah,
want more
it'd be good,
clarification,
actually.
we can easily talk about it.
I'd like to look at RCPP Armadillo as well. That looks amazing.
Yeah, I think it's pretty very, because because of the size of the data, so you can, and if you want to do that in high-res computational ratio, you've got to do some maybe write part of the code in C++ and using all these very clever libraries.
Yeah, no, it'd be really cool.
Well, just curious, what were your references at the end? You had two references, what were they? Are they about the methods or?
There is one about the, the first one is about the model itself, uncertainty stuff, then this other one is about the method. So about applying errors, labor Bayesian process.
Okay.
So I think this is directly very related to the stuff here, because of the nature of the data, you can easily do Bayesian process on such huge amount of data.